Hey everyone, and welcome. Today we're going to put on our detective hats and solve some of the oldest mysteries there are, the ones that are hidden right inside our own families. We're going to learn how to decode the patterns of inheritance using a really powerful tool. So let's get ready to follow the clues hidden in our family histories. Have you ever looked at your family and thought, wait, why do I have my grandpa's eyes, but my parents don't? Or maybe why a certain trait just seems to pop up out of nowhere? Well, these are all questions about heredity, and it turns out there's actually a map that can help us find the answers. So, every genetic investigation really starts with the same challenge. Why is it so darn hard to study human traits in the first place?
Well, unlike Gregor Mendel with his pea plants, scientists can't just set up experiments with people. I mean, think about it. Human generations take decades to unfold, and there are some really obvious ethical lines you just can't cross. Plus, family records aren't always complete. This is exactly why we need a clever workaround, a special tool for our investigation.
And that tool is the pedigree chart. This thing is the genetic detective's most essential piece of equipment. It's how we trace all the clues through a family's history. So what is it, exactly? Well, a pedigree is basically a family tree, but it's a special one. It's designed specifically to track a single trait, like, say, eye color, or a genetic disorder, as it's passed down from one generation to the next. You can think of it as a visual map of a family's genetic story. Now, to read this map, you've got to know its language, which is all about symbols. It's pretty simple, actually. A square represents a male and a circle represents a female. If a symbol is filled in, that person has the trait we're studying. If it's empty, they don't. And a half-filled symbol, that tells us they're a carrier, someone who has the gene but doesn't actually show the trait. The whole map is structured like a timeline. You'll see Roman numerals on the side. Those mark each generation. A horizontal line connects the parents, and then a vertical line drops down to their children, who are all listed by birth order. It's a really simple system that holds a ton of information. Okay, so now that we know how to read the map, it's time to start the real detective work, spotting the patterns that tell us how a trait is being inherited. This is where we learn to tell the difference between dominant and recessive traits. Let's look at these two cases side by side. On the left for Tay-Sachs, you see how those two unaffected parents in generation 2 have an affected child? That right there is a huge clue. Now look at the right for polydactyly. See how the trait appears in every single generation, and every affected kid has at least one affected parent? Spotting these patterns is the key to cracking the whole case. For a recessive trait, the biggest giveaway, the smoking gun, is when it skips a generation. Two parents who don't have the trait have a kid who does. That tells you both parents must be carriers. But for a dominant trait, it's the total opposite. It doesn't skip generations, and you can't get an affected child from two unaffected parents. These are the golden rules for your detective kit. And this is the real magic of the pedigree. Just by looking at the phenotypes, the physical traits that are filled in on the chart, we can make really good, educated guesses about the genotypes, the actual genetic code of each person. We're basically reading the family's genetic story without ever having to look at their DNA. Now let's see how these detective skills are used in the real world, because this isn't just some academic puzzle. This tool is right on the front lines of medicine, helping families understand and predict their risk for serious genetic conditions. So here are some pretty well-known recessive disorders. With every single one of these, like cystic fibrosis or Tay-Sachs, it's totally possible for the condition to just appear in a child, even if there's no recent family history. And that's precisely because parents can be silent carriers of the gene. But dominant traits can have their own mysteries too. Take achondroplasia, which is the most common form of dwarfism. Now, according to the rules, you'd expect an affected child to have an affected parent, right? But get this, a full 75% of cases appear in families with no history of the condition. So what's the culprit? A brand new, spontaneous mutation in the gene. And here we have some classic dominant disorders. Huntington's disease is a really tragic example where symptoms don't even show up until later in life. In a pedigree for Huntington's, you'll see it never skips generations. If a person has the disorder, one of their parents absolutely must have had it too. All right, you've learned the rules, you've seen the examples, now it's your turn. Let's put that newfound knowledge to the test and see if you can crack a few cases. First question, which of these statements about pedigrees is not true? What is something a pedigree can't do or isn't used for? Take a sec to look at the options.
And the correct answer here is A. As we've seen, pedigrees are super versatile tools. They're absolutely essential for tracking both dominant and recessive patterns of inheritance. Okay, next case for you. Imagine a pedigree where two unaffected parents have an affected child. Based on that pattern, which of these disorders could not possibly fit? Huntington's disease, D, is the one that just doesn't fit. Remember that golden rule for dominant disorders? An affected child has to have at least one affected parent. Two unaffected parents simply can't pass on a dominant trait that they don't have. All right, last one. Let's focus on that really key term, carrier. Which of these statements about a carrier is false? Right, the false statement here is B. By definition, a carrier is someone who doesn't have the disorder themselves. They carry that hidden recessive allele for it, but their normal dominant allele keeps it from being expressed. And that brings us to the end of our investigation. You see, the pedigree chart is so much more than just a family tree. It's a predictive tool. It empowers families and genetic counselors with real knowledge, turning what seems like a confusing pattern into clear probabilities. By learning to read these maps, we can all better understand the stories written in our genes. So, what genetic mystery in your own family would you want to map out?